Hello, my AP Chemistry icons. What we're going to talk about today is the idea of something called absorbance and transmittance. So to talk about what these are and why these are important, I want you to consider the two beakers that I've presented in front of you on the screen. So beaker 1 on the left and beaker 2 on the right. The only thing that's different about these pictures is the amount of lines that I've drawn into them. So here's what I want you to imagine. Imagine that I have these beakers with some water in them, and into them I have poured some solid. This solid's going to dissolve, and in beaker 1, I have poured less solid in, giving it a lower concentration. In beaker 2, I have poured more solid in, giving it a higher concentration. So we have been talking about this idea of something called spectroscopy and spectrophotometry, which is all about how light interacts with matter, right? So what we're specifically talking about here with spectrophotometry is how light is going to interact with the matter that's been dissolved into solutions. So the thing that's been dissolved, we are going to call our analyte. So that solid that I dissolved into the beakers is our analyte, and I want us to think about how light is going to interact with it. So let's say in beaker 1, I shine a light on this beaker, on the analyte in solution, and that amount of light I'm going to call I naught. This is just representing some number. The I stands for its intensity, how intense that light is, and I'm shining it into this beaker. So when I shine the light into this beaker, what's going to happen is it's going to interact with the molecules inside that beaker, and I'm going to get some light that comes out at the end. But it's not going to be the exact same amount of light that I put in. Well, maybe it is in some cases, but let's pretend in this case it's not the same amount of light. I'm going to call it I1 since this is beaker 1. So I put I naught light intensity in. I get out intensity I1 of light. Let's consider how this might be different for beaker 2. So let's say for beaker 2, I shine the exact same intensity of light into the beaker. In this beaker, there are more particles present in that solution. I have a higher concentration here, which means there's more molecules for that light to interact with. So I'm going to get some amount of light out, and it's not going to be the same amount of light I put in, and it's not going to be the same amount of light that came out of beaker 1. So I'm going to call this I2. So think about the difference between these two situations in your everyday life. If something that's more concentrated, it means it's going to have a darker color to it. It's going to be more opaque. It's going to be harder to see through. So when you're looking through that more concentrated solution, if you were looking out at the end of this situation here, so let's say your little eyeball's right here, you are not going to see as much light come through that solution because it's more opaque. There's more molecules that are blocking that light. In beaker 1, if you were to look at the end, out the other side of this beaker, there's less molecules that are dissolved into solution, less stuff for the light to interact with, so you're going to see more light that comes through. So hopefully that idea makes sense to you. So basically what I'm thinking about here is ranking these. I'm going to say that the intensity for beaker 2 is going to be less than the intensity for beaker 1 that comes out, because I will see less light out of beaker 2 since it's more concentrated. There's more stuff that's in solution. Let me give you one more scenario now. Let's go down to beaker 3. So what I've done with this beaker is I've taken it and I've elongated it. So now this light that I'm putting in, let's call it the same amount of light that I put into beakers 1 and 2, now has to travel all the way through this solution, and this solution is much longer. It has a farther distance to travel to get through to my eyeball at the other end. This is going to let some light out at the end, but it's going to be not the same amount that we got from I1 and I2. If this light has a longer distance to travel, let's say it's got the same concentration as beaker 2, so I'm just going to call it high since that's the concentration that beaker 2 was in. I have more molecules that I'm interacting with here, even though the concentration is the same, I have a longer distance for that light to travel, which means I'm more likely to lose some of it out at the end. So that means that I3, the intensity of the light that I get out here, is even less than that of I2. I3 is the least amount of light that's going to come through. It's got a far distance to travel, and it's got a lot of stuff in the way of it. So this brings us to this idea of something called transmittance. So transmittance is all about how much light gets through your system, gets through your solution, how much light is transmitted. And there's a mathematical quantity that's going to take us there. So transmittance is defined as the amount of light out divided by amount of light in. So this seems like a little bit of a weird definition, but I want you to kind of think about I'm really spelling it out, right? So the amount of light that you get out is what you see at the end of it. The amount of light that you put in is what we called I naught before. So if we were to define this in terms of beaker 1, transmittance for this beaker would be equal to the amount of light we got out, which we called intensity 1, divided by the amount of light we put in, we called intensity naught. So this is the mathematical function that relates the intensity of light to the transmittance, how much light is getting through. So if the transmittance if the intensity that we got out of beaker 1 is less than that of beaker 2, that also means the transmittance for beaker 2 is less than that of beaker 1. So I'm going to call this T1. The amount of light that we're getting out at the end is going to be less than the amount of light we put in, and it's even less than that situation for beaker 1 than it is for beaker 2, just because there's less molecules for everything to interact with. Okay, last thing that we're going to define before I tell you why are we talking about this, why do we even care, is something of the idea of absorbance. So transmittance is all about how much light do we get out, right? Absorbance is kind of like the opposite idea. It's how much light doesn't come out because it was absorbed by the system, absorbed by the molecules in the solution. So absorbance has a mathematical representation that we can relate to intensity, but we can also relate it to transmittance. Because these two are kind of opposite ideas, the way that we define absorption or absorbance, or I'm going to call it absorbance as well, that's another way you'll see it, is it's equal to the negative logarithm of your transmittance. So because transmittance can also be related to intensity, another way that we could potentially write this is the negative logarithm of the amount of light that we got out. I'll call that I1 for here, divided by the amount of light we put in, which we called I naught. So absorbance, how much light was absorbed by your solution. Transmittance, how much light came out of your solution. So why do we care about this? Why are we talking about it? Basically, this whole idea of spectroscopy, this whole branch of science, deals with how light interacts with matter. So if we know how much light we put into the solution and we can measure the light that came out, we can use this information to calculate the concentration of our solution. So this is just another way to help us get concentration, which is great. So what we can do to help us calculate this out is we can use an equation called the Beer-Lambert law. So the Beer-Lambert law relates the absorbance of a solution to certain properties of that solution. So let me define it for you. Beer-Lambert law says that absorbance, capital A, is, actually let me give you this one first, is proportional to the amount of distance, the length that your light has to travel. I learned it as lowercase b. I think it also can be written as lowercase l. But really all this is talking about is something called path length, which is how far does your light have to travel. It's also proportional to how far does your light have to travel times the concentration, C, of your solution. And concentration, we know, is in units, often units of molarity. For these systems, because sometimes you're working with such low concentrations, you may also see millimolar, which is lowercase m, capital M. So this is the relationship. This is how things are proportional, but this law, much like many of the other laws that we've seen, has something called a proportionality constant, because the way that light behaves with materials is very specific to the material that it's interacting with. So we can say, this is officially the Beer-Lambert law, is that absorbance is equal to epsilon, which looks like this. It's like a curvy E, times B, path length, times C, concentration, where E, epsilon, where E is dependent upon the material. So this is a property of the material. So it's specific to what you're working with. So why do we care about this? How can we use it? So basically what you can do is you can take some known concentrations of some substances, molarity, and what you can do is you can run it through your spectrophotometer. You can run it through your machine, your tool, to determine the absorbance. So what's very crucial about this is that light behaves very indicatively of materials based upon the color of that material. Color is an important property. So usually when you are measuring absorbance, it will be defined at some wavelength within that visible range. So you'll see an example of this when you get to the worksheet section, but normally you'll see this defined as like absorbance at X nanometers. So it tells you specifically like, oh, I'm tracking the absorbance at this wavelength. So what you can do is you can plug in with some known concentrations. Say you want to use like a 0.1 molar solution, a 0.2 molar solution, all that good stuff. And you can track its absorbance and say, oh, it showed up at this value right here. And then you can say, oh, well, I'm also going to do this at a 0.2 concentration, and it's going to show up at this value right here. Well, what you can do is you can create yourself a line. This will be a linear function. So you can connect these dots, boom, 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 and you can get your equation of your line to help you figure out at unknown concentrations, anything in the middle of these, anything that falls on that lines, you can run your solution, track its absorbance, and be able to determine the concentration. So say you ran some solution of unknown concentration and you found out that its absorbance fell right there on the graph. Well, you can track that over to your line and then extrapolate your data out and say, oh, my concentration was somewhere along those lines right there. Oof. I tried to make that at 0.2 and wow, I was very off. Really should use graph paper. That looks ugly. Anyway, you get the general idea of what I'm trying to say to you here. Basically, the Beer-Lambert law, the whole property of absorbance, the whole reason why it's important is because if we can track absorbance of some solutions by running them through a spectrophotometer, we can find the concentration of that solution. So what you're going to do next is you're going to work through that Beer's law worksheet to help you figure out how we can use Beer's law in the context of some like real actual lab problems.